Most people wait for electrical installations to smoke or a breaker to trip before they fix it. That is reactive maintenance, and it's expensive. Today, we are continuing with the PZEM-0040 and Node-RED IIoT preventive maintenance using machine learning to hear the cry for help from your electrical installations weeks before it fails. For example, when the mechanical side of a motor or pump starts to fail, maybe due to a dry bearing or load misalignment, the motor must work harder. This is reflected instantly in the electrical signature, indicated mainly by current. Most faults first appear as an increase in electrical current long before visible failure occurs. Preventive maintenance application of machine learning using the PZEM-0040 will allow us to detect the moment a failure begins, months before total functional failure occurs. Condition monitoring catches problems early by detecting deviations as small as 5% from the normal operating values. For this purpose, the condition monitoring nodes can be installed from the Manage Palette menu in Node-RED. This installation provides 8 nodes. However, today's focus is on anomaly detection. The anomaly detection node supports 7 methods for time series analysis, but we will consider the CUSUM or cumulative sum. It is designed to detect small persistent shifts in the average of the measured parameter, such as the electrical current. The current might only rise by 2 to 3%, which wouldn't trigger a standard alarm, but the CUSUM node will detect this cumulative trend and trigger an alert. Let's maintain the default drift settings, critical threshold, and warning threshold. The expected target current value may be specified, otherwise the mean value is calculated automatically. Connect a debug node to both outputs of the anomaly detection node, since the first output is classified as normal and the second is for warning or critical anomalies. Change the output properties of the debug node to complete message object. When the flow is deployed, CUSUM waiting and warm-up should be displayed below the node in succession. Then the CUSUM value of 0 is displayed if the expected value is unchanged. Observe that the debug messages show the various CUSUM output properties. The ones to note for now are the payload, which is the same as the current input, its anomaly, which could be true if a fault exists, severity, which could be normal, warning, or critical, and CUSUM pose, accumulated deviation from the target. To simulate current drift, connect an inject node to the anomaly detection node. Enter a number value of 0.07 and redeploy the flow. Click on the inject node once. Observe the change in the value of the CUSUM from 0, which gradually returns to 0 again due to the steady current stream from the energy monitor. When the inject node is clicked repeatedly, the CUSUM value increases until warning and critical are indicated successively. The status of these properties could be observed in the debug message window. We can show these anomaly properties on a dashboard with a text node. I will create a new UI group for preventive maintenance and select the same dashboard. Enter current as the label and the default message payload value. Duplicate the text node. Change the label to anomaly and the value to is anomaly. Copy and paste this node. Change the label and value to severity. And finally, CUSUM and CUSUM pose. Then deploy the flow. These preventive maintenance parameters can be monitored along with other power parameters and additional metrics, depending on the configuration. We are only just scratching the surface of preventive maintenance with machine learning. In the next episodes, we will explore how to configure the PZEM energy monitor and the ESP32 with the OpenPLC editor. Hit like and subscribe so you don't miss it, and let me know your thoughts in the comments. Bye for now.